Imagine turning 80 years old and your doctor tells you that, biologically, your body still looks and functions like it's 32. Not because you got lucky, because biological age, the actual measurable wear and tear on your cells, simply stopped climbing decades ago, even while your birthdays kept coming. One after another, a number that means less and less about what your body can actually do. Let's actually walk through what that life would look like. Not just the idea of it, the specific years, decade by decade, the actual shape of a life that stopped running out. 50 years from now. You're in your 70s by the calendar, but nothing about your Tuesday looks like anyone's 70s look today. You still remember your first job, your first apartment, the exact version of the world you grew up in, but you're living through the memory of all of it in a body that never got the message to start slowing down. No knees that ache on stairs. No 6-month recovery from a bad flu. You go for a run the morning after a long flight, the way you used to without thinking about it, and it still doesn't occur to you that this is supposed to get harder. You read the fine print on a menu without reaching for glasses you always swore you wouldn't need. Somewhere, a grandchild introduces you to a coworker, and the coworker assumes you're an older sibling. Here's the actual mechanism behind that. In 2012, a biologist named Shinya Yamanaka won the Nobel Prize for finding 4 molecules, now called the Yamanaka factors, that can take a fully adult, aged cell and reset it back to a blank slate, youthful state. For years, that was mostly a lab tool. But scientists have since started asking a more delicate question. What if you used those same factors not to fully reset a cell, but to partially rewind it, erasing the damage of aging without erasing what job the cell does? A heart cell that forgets it's tired without forgetting it's a heart cell. In 2020, geneticist David Sinclair at Harvard actually did this in mice. Partial reprogramming that measurably restored vision in old, vision-impaired mice. The eye cells didn't forget they were eye cells. They just forgot to be old. 100 years from now, your friend group includes people you met 90 years ago and people you met last month, and none of you look, move, or feel any different from each other. A reunion, a century out, doesn't feel like a reunion. It feels like nobody actually left the room. You've had, by now, 3 or 4 entirely different careers, not because you had to reinvent yourself out of necessity, but because 100 years is long enough to actually get bored of being good at just one thing. By now, the honest questions have gotten more personal, not less. How do you actually know a body engineered this way holds up past year 80, 90, 100? Nobody's lived through it long enough to be sure, because nobody could have until now. This is where the science gets genuinely uncertain. Not, will it work? But how do you prove something is safe across 100 years when the longest anyone's tracked it is a fraction of that? A scientist named Steve Horvath built the actual tool that lets researchers even ask this question. An epigenetic clock, a way to measure a cell's real biological age from chemical markers on its DNA, completely separate from birthdays. 2 people who are both technically 100 years old could have wildly different readings. One closer to a biological 40, one closer to 65. And for the first time, that difference is something you can actually track, year over year, instead of just guess at. And there's real risk sitting inside that uncertainty. Partial reprogramming, pushed too far, has caused cells in experiments to lose their identity entirely, or worse, start dividing uncontrollably, the same basic failure mode behind cancer. 100 years of staying on the right side of that line in one continuous human body is not a solved problem. It might not be solved for a long time. 1,000 years from now, here's the question that actually matters more than the biology. If your body simply never ran out, would 1,000 years still feel like something, or would it start feeling like waiting? The philosopher Bernard Williams asked something close to this back in 1973. He argued that a meaningful life runs on specific, personal reasons to want tomorrow. A project you're part way through, someone you're looking forward to seeing, something you haven't done yet but plan to. Given long enough, he thought, a person runs out of genuinely new versions of those reasons. Not because life gets worse, because a self only has so many truly new desires in it before it starts repeating ones it's already had, going through the motions of wanting things rather than actually wanting them. But maybe that's not the whole answer, because it assumes the world runs out of new things too, and it doesn't. 1,000 years from now, if you were still here, you'd have been alive for the first footprint on Mars. The first signal that actually comes back from somewhere past the edge of the solar system. The first close look at a planet nobody's ever seen up close, and the one after that, and the one after that. A body that stopped aging wouldn't need to invent reasons to keep going. It would just need to still be around when the next one happens. And there's never yet been a shortage of next ones. Scientists have actually watched a cell forget how old it was. Nobody knows yet what it would mean for a whole person to get to stay for everything that happens next. But for the first time, that's an actual open question, not a fantasy.